Hello class, today we're going to go over Unit 7, Lesson number 4, that's 7.4, Proving Trig Identities. So all of this process should be familiar to you from last year. The only thing that should be different is that now we have way more identities and formulas that we can work with and manipulate based on the last 3 lessons, 7.1 to all the way to 7.3. Okay, so I have put a copy of the formula sheet on the class website. It is basically the front page of this lesson here. So you will be given your reciprocal identities, right? So cosecant is 1 over sine theta, secant theta is 1 over cos theta, cotangent is 1 over tan theta. Your quotient identities, so again, these kind of 3 are the ones that we used last year. So your quotient identities is tan theta equals sine theta over cos theta, and then cotangent theta therefore is the reciprocal of this, so cos theta over sine theta. Our Pythagorean identity is sine squared theta plus cos squared theta equals 1. Keep in mind I always write at the side here for myself what the rearranged formulas would be if I isolated cos squared theta and sine squared theta, just so that my eyes can recognize it when I refer back to the sheet. We have 1 plus tan squared theta equals secant squared theta, and 1 plus cotangent squared theta equals cosecant squared theta. So the new ones from this year are double angle formulas. So remember, cos has the 3 versions, and our addition and subtraction formulas. Okay, so for sine a plus b, a minus b, and the same for cos and tan. And from the first lesson, these are the equivalent trig functions that you will be getting. So you will get your complementary angles, your horizontal translations, your symmetry, and your periodic functions. All right, so what is a trig identity? It's an identity that states the equivalence of 2 trig expressions. Okay, so it means whatever is happening here is going to be equal to here. So that means their graphs would be the same. Okay. It is written as an equation that involves trig ratios, and the solution set is all real numbers for which the expressions on both sides of the equation are defined. So if this so any theta values that's defined here, when I plug it into the theta values here, it has to be the same domain. Okay. As a result, the equation has an infinite number of solutions, right? So if the 2 sides are equal, then that means they create the same graph, which means they have an infinite number of points of intersection. All right, so students are always asking, how am I supposed to know what to do with a trig identity? You know, where do I start? How do I know what path to take? So I just gave you, I'm just going to go over here a few steps or some kind of key things you could look to try to do to simplify a side. Obviously, you always want to simplify the more complicated side first. And then after that, a lot of it is kind of like a puzzle, trial and error. So you might have to try a few things. Maybe it doesn't get you to where you want to be because you're always trying to get the other side to look like the side you're working on. So honestly, it may require a lot of patience and a lot of trials. All right, so some tips I have is that when you work with the complicated side first, this is often the side that may have brackets. So for example, if you have cos and then x minus y, okay? So this is usually a sign that maybe rewriting this to get rid of the bracket value here would be helpful. So remember, again, students will always think that cos gets distributed into both, and then it's cos x minus cos y. Remember, this is the subtraction formula, so you would rewrite this as cos x cos y plus sin x sin y. So that might help you out. The second tip is try to get rid of reciprocal functions. So for example, here if you see secant x, I usually find it's helpful when you try to translate everything to sine and cos if you can. So secant x, it might be helpful for you to rewrite that as 1 over cos x. The third tip, always look for terms from the Pythagorean identity. So for example, here we have cos squared x plus cos x plus sine squared x. So right away my eyes are looking at these two terms. This plus this, okay, is equal to 1. Okay, so this and this are 1 based on the Pythagorean identity. So I can rewrite this formula as 1 plus, and then that cos x stays. Okay. And another tip, try to get rid of double angles. So if I have somewhere in the formula, right, for example, it's sine 2x, it might be a good idea to help you simplify things by rewriting it in terms of without a double angle, so using your double angle formula. So writing it as 2 sine x cos x might help. Another thing that might be helpful is to try to write one side in terms of sine or cosine, just like I said. So if you've got like tan, for example, you might want to write that as sine over cos. Same thing for cotangent, write it as cos over sine. Usually simplifying it to sine and cos makes it a little more easy to manage. You're going to want to look for a common factor. So there might be a term that you can take out of both. So make sure you look for GCFs. Okay. If you are working with rational expressions, so if you've got some fractions and multiple terms being added or subtracted, you might need to find a common denominator in order to combine the terms. Okay. Once you have simplified one side to look exactly like the other, then you have to state that left side equals right side, or else your proof is not complete. Okay, so you have to put that in there. And remember, this is kind of a nice question because you already know what the answer should be. So it's just a way of, you know, finding the pieces to rewrite it to become that answer. Okay. All right, so let's dive into one. It says prove the following identities. When doing proofs, the proper form is to always separate left side and right side. You can do this T-chart that I do here where you separate them visually, or you can just write left side equals and then right side equals, but you do have to deal with them separately. You do not work with it like this. All right, so we've got tan theta, and we've got right side equals sine 2 theta and divided by 1 plus cos 2 theta. So immediately I think that the right side is the more complicated side. It's got some double angles here. And tan theta is pretty simplified. If you wanted to, all you could really do is rewrite it as sine theta over cos theta, or you can leave it as is and see what happens. So our first step is we definitely want to get rid of the double angle formulas in the top and in the bottom here. So I'm going to write the top as 2 sine theta cos theta. Please, when you're doing your identities, somewhere at the side of the page, do a side note telling me what identity from the formula sheet you used. So dA is just my short form for a double angle. And then at the bottom here, so this is where it's a little tricky. Cos 2 theta, I replaced with 2 cos squared theta minus 1. Okay, and you're probably wondering, well, why did she choose that one? There are 2 other versions of cos 2 theta. Okay, valid point. So obviously someone else could have tried one, manipulated it, maybe it didn't work. So a part of it is that you do have to kind of think ahead. So the reason I chose this formula is because I knew that the 1 here and the minus 1 in here would cancel each other out, thus simplifying it even more. So I was kind of foreseeing it. But like I said, you may not foresee that. You may plug in another one and maybe it doesn't work out well, and then you have to start again. Okay, so it's normal to be frustrated sometimes. All right, so like I just said, we're going to cancel out the 1 and negative 1. So then we're left with 2 sine theta cos theta over 2 cos squared theta. So remember, this just means that there's a cos theta times a cos theta. So that means we have a common factor of cos theta in the top and the bottom. This one had 2 down there, so that's why I crossed out the 2 and put a 1. So now there's just 1 cos theta left. And we have a common factor of 2 as well. That cancels out. Which means our last line is sine theta over cos theta. Okay. And we know based on the quotient identity that that's equal to tan theta. So therefore, we have just proven that left side equals right side. All right, let's try part B. So looking at this, the right side is as simplified as it's going to get, right? Negative sine x, can't do much with that. So this side here on the left is the more complicated side. So I can see that we've got some brackets here in the argument of cos. So let's try to rewrite this using the addition identity. Okay, so at the side here I wrote addition identity. So remember, this looks like cos A plus B, okay, where A is pi over 2 and B is x. So we rewrite that as cos pi over 2 cos x minus sine pi over 2 sine x. All right, so now that we have, when we have just x in there, or theta in there, we can't do anything with it because it's just an unknown variable. This is where we actually have an angle measure, so we can solve this. So cos pi over 2, so I want you to think of your cos graph. Right, so 1 and negative 1. Okay, so we know our cos graph does this. Okay. And right here, okay, is our pi over 2. And so we can see there that cos is equal to 0 at pi over 2. So we get 0 times cos x minus, and now we have to do sine. So sine at pi over 2 actually reaches its max. And it'll be like that in red. So sine at pi over 2 is at 1. So we have minus 1 times and then sine x. So obviously that term's going to cancel out. 0 times anything is 0. So we get 0 minus sine x. And that leaves us with negative sine x. And we are happy because that is the same thing as on the right side. Okay. So at the bottom, you're going to write, therefore, left side equals right side. So therefore, the identity has been proven. Okay, let's move on to the next one. So this one here, I've given a little hint, and it says that we are going to have to factor at some point here. Okay, so again, we can work with, they both have double angles in them, so we can, let's just work with the left side first because it definitely looks like it's the most complicated, and we'll see where it leads us. So the first thing you should be noticing is that there is a GCF here. Okay, so I'll just write it in. I know it's not an identity, but we took out a GCF of tan 2x. So we had a tan 2x here. So when we pulled it out, we're left with 1. And then we have a tan 2x here. And then when we pulled it out, we're left with negative 2 sine squared x. Okay. All right, the next thing we're going to do is, again, you might have to try a few different things. Our goal, remember, is to make it look like the right side. So the right side is a double angle formula for, is a double angle for sine. So let's try to see what we can do. Maybe we should maintain the 2x here to help us. So I noticed that 1 minus 2 sine squared x looks like cos 2x. So it's the double angle formula. Okay. The reason I'm doing this change and not rewriting tan 2x in terms of its double angle formula is because I'm already foreseeing that tan 2x's double angle formula is very complicated, and that might actually make my case worse. So that's why every scenario is different. So instead of doing that big, long rational expression, I'm going to rewrite this using the double angle formula. Okay. So this here is this here. Okay. All right, the next thing I think of is how can I rewrite tan 2x? So I think of the quotient identity. Okay, so the quotient identity says that tan 2x can be rewritten as sine 2x divided by cos 2x. Okay. This is helpful for us because then we have a common factor in the top and bottom. So we can cancel out the cos 2x's. So those two are gone. And then look at what we're left with. We are left with sine 2x. And that's already the right side, so we didn't even have to, rewrite its formula in here as well. So we are already done. So left side equals right side, and identity is proven. All right, part B. So definitely we can see here that the left side is the more complicated side because we can't do anything else with 1 minus cos theta on the right. So looking at this, we should be starting to think about how we can do some common factoring or other factoring rules. So I want you to notice that the 1 minus cos squared theta, hopefully you're noticing that that looks like a difference of squares, right? So two terms, both perfect squares, and both different signs, one positive, one negative. So let's rewrite the numerator as a difference of squares, okay? So 1 plus cos theta times 1 minus cos theta. Okay. The denominator, hopefully you can see in the denominator that the sine squared theta plus the cos squared theta, that's the Pythagorean identity. So we know those two add together to equal 1. Okay, so there in green has become 1. So the denominator is just 1 plus cos theta. So what's really cool about that is now you have a common factor in the top and bottom. So cancel out. And then we are just left with 1 minus cos theta. So that one was a quick one. Okay. All we did was factoring, difference of squares, and then we use the Pythagorean identity. And we can conclude left side equals right side, so we proved it. Okay, and let's turn over. All right, so a few things we can do here. Obviously, I always say start with the complicated side, so we're going to start with the right side here. We've got 1 minus tan squared x over 1 plus tan squared x. Those are two different expressions. We cannot cancel them out. So the first thing I kind of notice is that the 1 plus tan squared x is part of the Pythagorean identity. So if we go back to that first page, right here, 1 plus tan squared theta is secant squared theta. So I use the Pythagorean identity here to rewrite the denominator as secant squared x. All right. The next thing I decided to do was rewrite tan squared x in the numerator, so I'm just looking at the numerator right now, as in terms of its sine and cos. So once we do this, I want you guys to now rewrite tan x and secant x in terms of sine and cos, okay? So tan squared x would be sine squared x over cos squared x. Okay, so just look at the green for now. That's the quotient identity. And then I'm going to rewrite secant squared x as 1 over cos squared x, and that's using the reciprocal identity. Okay. So that's for here, that's for here, and reciprocal identity is down here. Okay. All right, so I know it looks very ugly. A lot of them may when they have lots of fractions like this. Now I want you to work with the numerator. Okay, so the numerator is 1 minus and then sine squared x over cos squared x. So the only way I can simplify this numerator is if I find a lowest common denominator. Okay, so we're finding a lowest common denominator of with 1 and cos squared x. Well, that has to be cos squared x. So I have to multiply the top and bottom by cos squared x. Okay. So what does that give me in the numerator here? Okay, so that means I get cos squared x minus sine squared x all over the common denominator of cos squared x. Okay. Now we still have to deal with the denominator, okay, and that's still 1 over cos squared x. So because we're dividing these two fractions, When I keep this the same, switch to multiplication, and take the reciprocal of the bottom fraction, what's going to happen is you're going to have a cos squared x up top and a cos squared x at the bottom. So we can actually cancel these out. So cancel, cancel, and then you're going to see that you're left with cos squared x minus sine squared x all over an imaginary 1. And hopefully you guys recognize that that is the double angle formula, one of the versions of cos 2x. And we are happy. That is the left side that we were looking for. So we have proven left side equals right side. All right, this one, part D. So there's a few ways you can kind of go about this. Obviously, both of them here kind of look complicated, right? We've got tans here, and then we've got some subtraction and addition formulas here. So you might have to, like I said, maybe someone started with left side, someone else started with right side. Hopefully you can get to the same place. Sometimes you can get to the same place using different methods. Sometimes the different method will not work, and then you have to go back and try something else, okay? So I decided to work with the right side. It was dealing with tan. So this is what I decided to do. Okay, so I know it looks a little busy here. So I rewrote the numerator, 1 plus tan x tan y. So I'll just look at the numerator here. Okay. I decided to rewrite tan x and tan y in terms of sine and cos. Okay, so I used the quotient identity. Okay, so I did 1 plus sine x over cos x times sine y over cos y. All right, so again, like in the previous example, I won't be able to simplify the numerator in the next step until I write it all as one term. And I can't do that until I find a lowest common denominator. So the denominator with these two multiplied is cos x, cos y. The denominator of 1 is 1. So that means I have to multiply the top and bottom here by cos x, cos y. All right, I'm going to do now the exact same thing with the denominator. So 1 minus tan x tan y, I'm going to use the quotient identity again and write it as 1 minus sine x cos x times sine y cos y. Just the same as with the numerator, I need to find a common denominator in order to combine the bottom. So I multiply top and bottom of 1 over 1 by cos x cos y. All right, so what does that leave us with? That leaves us with a numerator, so let's just look at the numerator here, of cos x cos y plus sine x sine y, all over the denominator, the LCD of cos x cos y. The denominator of this guy here, okay, will give us cos x cos y minus sine x sine y all over the LCD. So again, we have a fraction divided by a fraction. So when I leave this the same, change to multiplication, and then flip the bottom, what's going to happen is that cos x cos y is going to go up top, and this guy's going to stay in the bottom, so they are common factors, they can be canceled out. So then I'm left with cos x cos y plus sine x sine y divided by cos x cos y times sine x sine y. Hopefully you are noticing that this looks like, okay, so the numerator has coses together, sines together, and separated by a plus. So that looks like cos x minus y, because the cos always switches the sign. And then the denominator, coses are together, sines are together, separated by a minus. So that means the bottom is cos x plus y. And that is exactly what the left side was. So we have just proven that left side equals right side. Okay, so identity proven. Okay. Right, so that was an example of how finding a common denominator is beneficial to you. All right, and lastly here, it says prove that the following, oh sorry, let me start here. If you have to prove that something is not an identity, all you have to do, so if I say prove something is not an identity, all you need is one counterexample. So that means if you substitute in a value for x, that disproves the equivalence. So basically you want to see what x value can I sub in that would make left side not equal to right side. Okay. The minute you find one thing where they don't overlap, then they obviously can't be equivalent. Okay. Keep in mind that if you were to prove equivalency, subbing in a value and getting left side equals right side does not mean that they're equivalent. It could just be, that point could just be the point of intersection between two functions. Okay, so that's why proving trig identities has to be done in this way, because you can't spend all day testing every single x value. Whereas if you have to disprove something, okay, prove something's not an identity, all you need to do is prove once that x does, that the left side does not equal right side. Okay. So here's an example of disproving. So we have to disprove 1 plus tan squared x times sine squared x equals 1. So again, you might have to try a few values. So I decided to sub in x equals 0. Okay, so when I sub in x equals 0 for left side, okay, so that's our left side. There's a few things you can do first, by the way. If you want, you can simplify it first using identities. Excuse me, it does not matter. So for example, I rewrote 1 plus tan squared x as secant squared x. And then I rewrote secant squared x as 1 over cos squared x. Okay, so this one here, I use the Pythagorean identity. Okay, and then I use the reciprocal identity here. And you're going to see, then I started to plug in 0. Just if you wanted to work with that, or you can plug it in right away, okay? It does not matter. So 1 divided by cos 0 squared times sine 0 squared. So cos at 0 is 1, so that would be 1 over 1 squared, okay? And then multiplied by sine at 0 is 0, so 0 squared, so anything times 0 will give me 0. So when I let x equal 0, the left side equals 0, and the right side, though, is said to always be equal to 1. So therefore, left side does not equal right side, so therefore not an identity. Okay, so that was enough to prove it. All right, and part B. It says sine x plus sine 2x equals sine 3x. Okay, so remember, these are not like terms. Okay, they cannot be combined together. This one has a k-value of 1, that one has a k-value of 2. And that one is 3. So a lot of times students will say, Miss, let's plug in x equals 0 again for this one. I want you to visualize why x equals 0 will not be a good counter example. Okay, so if I plugged in 0 here, 0 here, 0 here, what's going to happen? Okay, so if you let x equals 0, what's going to happen is that your left side is going to be sine 0 plus sine 2 times 0, so that's 0 plus 0. Okay. And then your right side is going to be sine of 3 times 0, so that's just sine of 0. So you get left side equals right side. So this is not good because this is not a counterexample, right? So what this means is that if I were to graph the left side and right side, I just found out that they would intersect when x was 0. So that just happens to be a POI. Okay, so I need to test another angle value so that I can disprove it. So the next value I try is x equals pi over 2. Okay, so when I plug that in, so I'm going to do for left side sine pi over 2 plus sine of 2 times pi over 2. Okay. The 2's are going to cancel out here. Okay, so I'm going to be left with sine of pi. Okay. So sine of pi over 2, that's when it reaches its max, so at 1 is the y value. And sine of pi is when it comes back and crosses the x-axis, so that's 0. So I get 1 plus 0, so I get left side equals 1. Right side. So I'm going to sub in sine of 3 times pi over 2. Okay, sine 3 pi over 2. So 3 pi over 2 is when it reaches its minimum. okay, and its minimum value is -1. So this is a good counterexample because I've shown that left side does not equal right side, okay? Therefore, it is not an identity. All right. So really all I can advise, go over some of these tricks that I've done in these examples. And with identities, the best thing you can do is practice, practice, practice. And eventually kind of the puzzle pieces, and you're going to notice like common tricks that you can use to help yourself get to the right answer. Please let me know if you have any questions, and good luck with the homework.